In this video, we will discuss about the most famous normal distribution. We will start the understanding from the one we already discussed in the earlier video, which is binomial distribution. Let's suppose there is a random variable x which is following binomial distribution with parameters 10 and 0.5. So here n is 10 and p is 0.5 or half. So x can take value from 0 to 10. We will now find the individual probabilities corresponding to x equals to 0, 1, 2 up to 10. So first, just write down these things. We are going to calculate probability of x equals to 0, x equals to 1, x equals to 2 and up to x equals to 5 at first. So we will just put the formulas here. I am not explaining everything. I hope that you have seen the video on binomial distribution and you can easily figure out that how am I write these formulas. So quickly I am writing down the formulas and then the values also. So probability of x equals to 0 means 1 into 1 by 1024. X equals to 1 is 10 into 1 by 1024 and like that up to x equals to 5, which is 252 into 1 by 1024. So also note that probability x equals to 0 is same as probability x equals to 10. Likewise, x equals to 1 is same as x equals to 9. And at the end, probability x equals to 5 is of course equal to probability of x equals to 5. Now observe that apart from the factor 1024, 1 by 1024, the probability of x equals to 0, 1, 2, 3, 4, 5 increases as we go from 0 to 5. So we are now plotting these values, plotting p of x with respect to the value of x, which can be from 0 to 10, and we are just making a rough plot. So for probability x equals to 5, it will be highest, and for x equals to 4 and 6, they will be equal, slightly lesser than probability of 5, and 7 and 3 will be equal, and similarly 8 and 2 will be equal, and as we go along, the probabilities will get lesser and lesser up to we have put 0 and 10. So this is a rough plot that I have made, and the probabilities follow this kind of a curve. This is called a bell curve. I have also plotted the same thing on a graphing software called Desmos, and this is the graph I am showing in the screen right now. As you can see, the shape of this curve, which is plotted in the software, matching very well with the estimated curve we have drawn earlier. And this is the same distribution. X follows binomial 10, 0.5, and in the x-axis we have written the points x can take from 0 to 10, and in the y-axis is the probability of x. So now in this figure, I have plotted x following binomial 100, 0.5. So just the number of points is increased from 10 to 100. And in the x-axis, the left hand side goes towards 0 and the right side goes towards 100. The possible values x can take, and in the y-axis it is probability of x. Notice that for x equals to 50, the probability is maximum, and it is decreasing if x goes more than 50 as well as less than 50 towards both the sides. So next, I have plotted another graph, and this is of a binomial distribution with parameters 1000 and 0.5. So again, just the number of points is increased. And in the x-axis, it is the same thing. Towards right it is 1000 and towards left it is 0. And notice that for the point corresponding to 500, the probability is maximum, probability of x is maximum, and it is decreasing in both the sides. This is again the same thing. Now the number of points is increased to 10,000. Okay, so now the graph almost looks like a continuous graph because the possible points x can take is very large now, and the graph is naturally taking a very particular shape. This kind of curve, as I have said earlier, is called a bell curve. So the point I am trying to make here is, if you increase the number n in a binomial distribution, the probability function takes a particular shape, and as the number of possible points x can take becomes larger and larger, this curve looks like a continuous curve. So now I will just write down the summary. As n tends to infinity, binomial distribution takes a special form which is called a normal distribution. Also, there is one note that binomial distribution is a discrete distribution because x can take discrete values, but as n goes to infinity, x becomes almost like continuous, like in the figure, and that is the reason normal distribution is a continuous distribution. We will now formally define the normal distribution here. So if a random variable x follows normal distribution with parameters mu and sigma square, then the density function of that random variable, remember it will be a continuous function, fx equals to 1 by sigma root 2 pi e to the power minus x minus mu square by 2 sigma square. This is the what I can say the probably most famous distribution function in all statistics. So you have to remember this, and remember that x can take values from minus infinity to plus infinity here. Now the mean of x, which is also called the expectation of x, is mu, and the variance of this random distribution of this random variable expectation of x minus mu square is equals to sigma square. So notice that this mu and sigma square, these are the parameters by which the normal distribution is defined. It is written in the first line, x follows normal mu sigma square. Now there is coefficient of skewness. So as we have guessed from the normal curve, alpha 3 will be 0. Then coefficient of Kartusis for a normal distribution is alpha 4 equals to 3. And moment generating function, we will show it later that how these results are coming. So for now, just remember them as a formula. So moment generating function mxt equals to e to the power mu t plus sigma square t square by 2. And then the characteristic function, which will be remembered from the moment generating function easily. So phi x omega is just replace I omega in place of t in the moment generating function. So e to the power I mu omega minus sigma square omega square by 2. Now the next important topic is standard normal distribution, which is, as the name suggests, simply a standardized normal distribution. So we are defining it like this. So if x follows normal mu sigma square with mean equals to mu and variance equals to sigma square, then we define a new distribution z, which is x minus mu by sigma, and this will follow normal 0, 1. So this distribution z equal to x minus mu by sigma has mean 0 and variance 1. That is why it is following normal 0, 1. So the parameters are 0 and 1 here for a standard normal distribution. So the density function of Z will be easy to write. Just put mu equals to 0 and sigma equals to 1 in place of the density function of normal distribution. So fz equals to 1 by root 2 pi e to the power minus z square by 2. We will have to remember this as well. The probability density function of a standard normal distribution will look somewhat like this, that I am trying to draw on my hand, so just pardon me for any mistakes. So the y-axis is the fz probabilities and x-axis contains z. See that mean 0 is in the middle, and in the both sides I am writing 1, 2, 3, and in the left side minus 1, minus 2, minus 3. So now in this region from plus 1 to minus 1, the probability that z will remain in this region is 68.27%. Similarly, the probability that for a random variable z, the value it can take from minus 2 to plus 2 is 95.45%. The chance of z lying between 3 and minus 3 likewise is very high, which is 99.73%, almost 100%. So if you write this in mathematical terms, so the probability that z lies between minus 1 and plus 1 is 0.6827. Similarly, probability that z lies between minus 2 to plus 2 is 0.9545, and the same that z lies between minus 3 to plus 3 is 0.9973. So these are very well defined result in a standard normal distribution, and people generally have to remember these things, and you will also see in the later stage how to calculate this. So just note that the expectation of z, mean of z is 0 and variance of z is 1. That is the property of a standard normal distribution, and the curve has the peak at the exact point mu, which is 0 in this case. So in general, for any normal distribution x, not only standard normal distribution, it can be shown that probability that any normal distribution x will be within one standard deviation away from its mean, the probability of that is 0.68. Similarly, the x is within 2 standard deviation away from its mean is 0.95, and x is 3 standard deviation away from its mean is almost close to 1, 0.99. Now we will finish this part just going back to the point from where we have started this video, the relationship between binomial and a normal distribution. We will formally write it down at this stage. So if x is a random variable which is following binomial distribution with parameters n and p, so the mean of x is np and variance of x is npq, then as n tends to infinity and p and q both of them are not very close to 0, then if we define x minus np by root over of npq as z, then z will follow standardized normal distribution. So here z is a standard normal distribution and x minus np by root over of npq is a standardized binomial distribution. And this will happen if n tends to infinity and p and q both are not very small. So just look at this again. So at the limiting case when n tends to infinity, then the standardized binomial distribution x minus np mean by root over of npq, the standard deviation. So x minus np by root over of npq is the standardized binomial distribution. So in this limiting case, standardized binomial distribution is equal to a standard normal distribution. So here is the most important relationship between binomial and normal distribution. And at this point we will end the video for today. See you in the next one.